we're going to be doing this coming week, we're going to be doing chapter 12. And chapter 12 has just basically got one theme, and that is hypothesis testing of proportions. And the chapter after that, which we'll do next week, and actually the chapter after that is the last chapter, so we'll do it all the way to the end, is hypothesis testing of means. So everything from now on to the end of the quarter is all about hypothesis testing. So let's try and give you a kind of a big picture on this. There are a lot of people who find getting to grips with hypothesis testing is a little bit difficult for them, right? It's a little bit challenging, and I can understand why. It's a very formal way of setting up, is there enough proof to prove something, right? Is there enough evidence to prove something is true? That's what hypothesis testing does. And all the hypothesis testing that we're going to do, we're going to be doing today single proportions, and over the week, difference between two proportions. So this week it's all about hypothesis testing and proportions. All of them follow these 5 major steps. And next week, we still follow these 5 steps. What essentially happened historically is that when people would argue, oh, look, I've done this sample and I've proved that, whatever it is, left-handed people are better at tennis than right-handed people, or there's enough evidence to prove that this theory is true or that theory is true. There was an awful lot of subjectivity in it. What you thought was evidence, we know from experience, could have just been an unusually atypical sample that you'd got, right? You got a sample and it just came out weird, and these happen.
In progress.
And so what we needed to do is we had to formalize a scientific, very structured way of how do you prove things. And this is called hypothesis testing. And it's pretty much accepted everywhere in the world that I know of. And they all kind of got together and agreed, these are the steps that you would take. The first step is, once we've gone through these 5, we're going to look at is find what's called the null and the alternate hypothesis. The null hypothesis is basically, there's nothing to see here, you haven't proved anything, nothing has changed, right? Left-handed people are just as good as bad at playing tennis as right-handed people, right? There's nothing to see here, that's the same. The alternate hypothesis is always going to be what you hoped to prove. You've always got this idea, I think something's true, I hope something's true, right? You want to prove it. That's going to be what we call the alternate hypothesis. So in my story about tennis players, the null hypothesis would be left and right-handed tennis players are just as likely be as good as any other. And then my alternate would be left-handed tennis players are better than right-handed tennis players, right? That would be the thing I could hope to prove. Step 2, which we should get to today, in fact, I know we will, we're going to find what's called the test statistic. But you know this guy. Do you recognize p hat? Right. If I wanted to prove that left-handed tennis players were better than right-handed tennis players, couldn't one way to do that would be to collect a random sample of left and right-handed players and let them play each other and see how many times the left-handed one and how many times the right-handed person won, right? Now, if left and right-handedness didn't matter, wouldn't a left-handed person win about 50% of the time? Right, and lose the other 50, right? But if there was evidence, wouldn't the left-handed people win more than half the time, right? So we need to collect information, right? Data, and that's the sample, and that's going to be p hat. Also in this step, we verify whether you can conduct the test in the first place. You know, when you do tests, any kind of collection of data, Shouldn't you have a list of things that has to be true? For instance, doesn't the sample have to be big enough? But if I wanted to do the left and right-handed tennis player thing, do you think it would be a good idea if I only got one left-handed and one right-handed and said, right, play a game and let's see who wins? Would you agree the sample size is tiny there? That's not good. Don't you want hundreds and hundreds, the more the better? So that would be one. But aren't there other things, depending on the context, that you won't be aware of there? Don't you want your sample not only to be big, but to be a fair representation of the population? And don't you also want your sample to be, when you ask, if it's a question that you're asking, that you ask it in an unbiased way? So all the kind of things that you would usually do happen here to make sure that your sample's a good, fair, representative sample. Now, these guys here are really not going to make a lot of sense yet, because we probably won't get to these steps here. Maybe that one we'll see, but we won't get to that until Wednesday. But we're going to look at finding what's called a p-value. And a p-value is the probability that you get your test statistic in the world that the null hypothesis says is true. So it's basically, I collect a sample, and what's the chances that a left-handed person wins, and it's 60% of the time. Wouldn't 60% be interesting? It would be better than 50. So there's probably something going on. And then you make a conclusion based on this p-value and another guy you don't know about yet called significance level. And then when you're finished, you state what your conclusion is in English. Right? So you say, I have shown, or I have proven, that left-handed players are better at tennis than right-handed players, right? If that's where I was going, right? That might be my answer. My other answer might be, I haven't found any evidence to prove that left-handed players are better or worse than right-handed players, right? So you tend to have two choices for your conclusion. One is you've actually proven something, and the other is you didn't find evidence to prove it. Okay, let's start with step one then. Step one is find a null and alternate hypothesis. So they are called H0 and HA. H0 is called the null hypothesis. And this is called the alternate hypothesis. Null hypothesis is basically the status quo. What I mean by that is nothing has changed, or nothing is different. Some just fell over. Now, the alternate hypothesis is that we believe that something has changed or something is different. In some way. So it's very cryptic because there's lots of different stories you can get, so you can't really focus on one. So far so good. Let's put that into practice. There are, in fact, 3 versions of a hypothesis, null hypothesis. Here's the first one. In 1900, 80% of Americans were in favor of the death penalty. So way back in the day, in the 1900s, 80% of Americans, adults, if you asked them, are you in favor of the death penalty? They would say, yes, I am. And a social scientist would think, America has changed in the last 100 years, right? I believe that that number is now less. So I believe it is now less than 80%. So let's see how that becomes a null and alternate hypothesis. P represents the proportion of the population who are in favour of the death penalty. The null hypothesis is that it hasn't changed. It's still the same number it was in 1900s. It's still today, right? Monday to right now, 80%. The alternate is what this guy believes. He believes it is now less than 80. So do you see how your null hypothesis says nothing's changed? Now you see here, it's the same as it always was. And the alternate is, I believe it's different. How do you believe it's different? I believe it's got less in this story. Now we have some names for these guys, so let's introduce the name. When you have a test like this, we call it a left-tailed test. And we'll just leave it at that for the time being. Later on, not today, but later on, I'll show you why it's called that, not any other name. It's called a left-tailed test. If you want to remember how it works, do you see how that's pointing to the left? It's a little symbol pointing to the left. That's an easy way to remember. Right. So that's our first one. That is, have you found evidence to prove something's different? And the difference is it's now smaller than it used to be. Okay. Now, second story. In the last election, 45% said that they had voted Republican, right? That was in the last election, 45. Is there evidence that today more people would vote Republican? So, whatever it was, 2 years ago, 45% voted Republican. Is there evidence that today more people would vote Republican? So we have a null hypothesis and an alternate. The null is always going to be P equals, regardless of what this textbook tells you. It's always P equals. What number will it be equal to based on what's written here? Agreed. Are we all happy about where the 0.45 comes from? Are we good? Now, sometimes in the textbook, they will also put beside it, or P, I know, less than 0.45 or something like that. Well, you just pretend that you never saw that, because nobody really does it except this textbook, and I don't want us to get bad habits. So always think of the null as being equal and you'll be fine. Now, what would the alternate be based on what this particular person who's going to be conducting the survey thinks is going to be out there? Right. So would you agree? We believe that there should be evidence that it's now more than 45%. What name do you think we give to a test that looks like that, based on what we call this test?
Right tail test.
Yeah. And right now, you're just saying, okay, that's what you call them. But isn't it pointing to the right? So that's an easy way to remember. And so there's your first kind, equal to 0.8, less than that, equal to a number more than that. And the third possibility is coming up right now.
Hey, Professor.
Yes.
Two people are trying to get into the class and they
Oh.
can't seem to.
Oh, thank you. Well, there's nobody there right now. I wonder if they've got in. I'm assuming that you know because they shot you an email saying I'm trying to get in and I can't. Okay, I'll keep an eye on that in case they turn back in. They might be having electric issues. Oh, it's still the third one to do. And let's see, I've got a story over here. Can I use it? Okay, in this third story, a country had, or has, I guess, 25% of the population were overweight. But that was in the year 2000. Oh, here's Isabel getting in, so there's one person made it. And this time the question they want to find evidence for, is there evidence that it's now changed? Have you heard the COVID-19 rule? No, I read it somewhere. It's kind of cool. COVID-19 rule means that a lot of people have gained 19 pounds because they've been at home and not doing stuff. And COVID-19 is kind of a shortcut. And that might well be true. So can you imagine this might be a COVID-19 rule, right? 25% of you were overweight in what, 2 years ago, but in this story it's 2000. Is there evidence that it's now changed? Because maybe you lost weight. Ah, yes, you know, good on. So let's set up the null hypothesis and the alternate hypothesis. The null hypothesis will always start with P equals. And would you agree that it's this here? How do you think you represent, is there evidence that it's changed? They didn't say it's changed and got bigger. They didn't say it changed and got less. They just said they think it's different, right? It's changed. How would you write that?
Not equal to 0.25?
Correct. Yes. Now that's the symbol that we use in mathematics for not equal to. Hopefully you've seen that symbol somewhere. A little idiosyncrasy of WebAssign. Did it wrong way around. Evidently, WebAssign does not have a not equals to button. So you have to write down exclamation mark equals when you want to do not equals, okay? Just something to remember, because some of your answers are going to be that. If this is called left-tailed and this is called right-tailed, any guesses what this is called?
Tailed.
Say that word again, Aidan.
Tailed.
Close. I'm going to put that in because that's part of it. Stick a word at the front and we got it.
G-tailed test?
Yeah. Are we looking good? So if I gave you a story, would you be able to tell me the null and alternate hypothesis? And could you tell me if it was left-tailed, right-tailed, or two-tailed as well? It's kind of all we've done so far. We feel comfortable with those. Okay, so let's go and look at some homework questions to see how they can make our life awkward when they didn't need to. course, I have to take the keys off because it always has the keys. Right, can you read that okay?
I can read it, but the key is still on.
You're right, it is. I thought I'd taken it off. Evidently I hadn't. Right. Okay, you read it good now? Right, let's see, can I make that bigger? You win some, you lose some. Okay. Here is a story that said in a previous example, hypothesized that the proportion of babies born during the full moon is 1/29.53. This is based on the fact that on average, a full moon occurs 29.53 days. It's probably something to do with the fact that a year is 365 and a quarter and divide it and all that good stuff, right? So we could easily classify babies as to whether or not they were born during a 24-hour period surrounding the full moon. And the hypothesis of interest here is that the proportion of babies born during the full moon is that number. So that's basically just us setting up the null hypothesis. They don't even have an assumption about what it might be. Maybe if you worked in the hospitals, you might say, you know, I think when it's a full moon, we get more babies born, or we get fewer babies born, or something, right? That would be the alternative. But in this case, we don't have them. Why have I still got numbers on these? Go away. Okay, I may have just accidentally clicked on them, so that's fine. Right. I'll just pick the top dot and then we can move as required. What is the population of interest in this story? So, which one of those?
All the babies.
All the babies. What is the population parameter of interest? So what are we trying to find out about these babies? Actually, isn't it the one I'm on right now? Now, what is H naught? H naught will be P is equal to, and it's that ugly 29.53, guys. So fraction button, 1, 29.53. Okay. Now I'll put it back in the top one. Professional tennis players, Martina Navratilova and a whole load of other ones, are all left-handed. Did you know that they were left-handed? Which is where my idea of left-handed comes from. Do you know that the experiment I was pretending at the start, I think that might be quite interesting to do. Right. If you took the top 100 tennis players, maybe more of them are left-handed than are left-handed in the general population, right? So the null hypothesis would be P is 0.2, but for tennis players, it's bigger than that because more of them are good at their job. So you could do that. Now, the population of interest here is all current and retired professional tennis players who are not left-handed. Isn't it the ones who are? Right. Write a hypothesis in words before and all the usual stuff. Researchers are interested. Oh, let's read on the story. I should keep going. Define the parameter P as a proportion of tennis players current and retired who are left-handed, which is why I chose that answer, right? And researchers are interested in the hypothesis that this is bigger than 10%. Okay. Researchers are interested in the hypothesis that the proportion of current and retired professional players who are left-handed is greater than 0.1. I got lucky, it's the first up. Okay, now, you will totally ignore those guys.
Hey, Professor,
Yes.
for that second answer, or for part A of that last question, it's saying that is not correct.
It is.
Mhm. The population of interest of all current and retired professional tennis players who are
Well,
left-handed.
the population of interest is all tennis players. Oh, I misread the story.
Okay.
There it is. This dot here is correct. Isabel, you seem to be bouncing out and in. You must be having issues. Right. Try and ignore the fact that the null hypothesis has a greater than or equal to and a less than or equal to. When you see them, will you just see 0.5 and 0.3? Just trust me, you better do it. Okay, I'm getting answers here all over the place. I'm going to close this and go back in because I don't like all those answers and they're distracting the heck out of me. So bear with me for a few minutes. Now I'll get back to that question that's driving me crazy. Right. Are you looking at the questions again? Okay, good. So the null hypothesis is that's good. It's a two-sided test. If it's a two-sided test, what do we do about the P? Bigger than 0.25, less than 0.25, or not equal to? What do you do when it's a two-tailer? Right. Now to get not equals, we'll have to do that funny exclamation mark equals, right? And if we do that, we can then put in 0.25. Now, if they really wanted to do this question, a better way of doing it would have been just to tell you P is 0.4, and they want to know an alternate where it's bigger than 0.4. Thank goodness they don't do that too often. That's the end of those. Okay, so here we have a story where we're going to set up, but it's going to be in English, a null and an alternate hypothesis. And the story goes like this. Will an increase in speed limits on an interstate highway lead to an increase in highway fatality rate? Right. Okay. So the null hypothesis would be no effect, right? Increasing the speed doesn't increase fatality rate, right? So I'm going to see if I can find that to choose up. We'll forget that one. Right, now it might be that one, right? Increasing speed limits on interstate highway does not increase fatality rate. Now what's the alternate? Well, this person thinks that it's going to make it worse, right? Increasing it. And to make it worse then, increase speed limits, increases the fatality. Ah, got it. It's that one. The null hypothesis, increasing speed limits doesn't have any effect. That's the top one. Alternate is that increasing the speed limits increases the fatality rate. If you read the story basically from here to here, isn't all of that contained inside those two statements? That's kind of how you have to do these things. They're kind of like reading lawyer documents. Right. Is this going to be a one-sided? That's not good. One of my screens just went blank. Now both my screens have gone blank.
My
And
power flickered, so I think the wind is probably messing with things.
I'm pretty
Yeah,
sure.
my
Right.
power just flickered a whole bunch.
Yeah.
Yeah,
Dang.
my entire house just flickered, so.
We're all in the same boat, so we're all going to try as best we can. There's another one. Get through this as quickly as we can, or at least as much as I can. Right.
I had to switch my phone for data.
So there's one-sided. And here's a different story. A coin is spun, and what's the probability it will land heads up is equal to 0.5. So what would the alternate be to you throw a coin and the chances you get a head in this story? Right. Null is it's ahead, not equal to, right? That's a little cross. So I'm looking for is 0.5 and is not 0.5. Do you call that a one or a two-sided? Agreed, not equals, two-sided. Oh, here's our first story with some numbers. Suppose that the present success rate for a particular treatment is 67%. A research group hopes to demonstrate that the success rate of a new treatment is better than that. So the null hypothesis is that the new treatment doesn't do anything better, right? It's still 0.67. The alternate is it's an improvement. Oh, shooting space. There we are. You see how we set up the null and alternate? The null is nothing's happening here, still 0.67. The alternate is this is better, bigger than 0.67. And we are going to do this test in the class. So I'm going to close this off for a second. And we are going to do once I figure out where all my buttons are. Oh no, darn it, go away. Go away. Right. Can I see every? No, I can't see everybody. I need to go and view. I need to see us all. No, that's not good. When that flicker happened, it's buggered up my windows. So that's not making my life any easier than it should be. Okay, we're going to do this vote a different way. There's numbers, digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 0 to 9. You are going to go into the chat and you are going to tell me what number you just thought of. So while you're typing that in, I'm going to make some predictions.
Did you say 1 through 10?
1 through 9.
Okay.
Okay, I've made my predictions. Everybody who's taken part has taken part. And it'll take me a few moments to collect the data, but that's fine. Okay, so I'll start at the top. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9.
This is a weird side note, but I've noticed, like, I've just noticed in general, a lot of people's favorite number, the number they say most often, is 7.
It is not. That is exactly what I was expecting. I've written down here 3 different things. I'll tell you my predictions right now before I even collect them. 0 is going to be the least common choice. Very few of you are going to pick 0. 7 of you are a lot of you are going to pick 7. That's a very common choice. And last but not least, odd numbers are going to get picked more often than even numbers, right? So that's my prediction. So here goes. I'll try and do this quickly as best I can. And here goes. First one was a 3. Move down, another 3, then a 5. I go down a bit more. It's a 2, 8, and 7. 2, 8, and 7. We go a little bit more. It's 3, 7, 7, 7. 3, 7, 7, 7. Then it's 2 more 7s and a 1. Then it's a 9, a 6, and a 6. A 5, a 7, and a 7. A 7, a 7, a 7, a 7, a 7, a 7. A 3 to finish with. Right, let's see if I can show you those results. There they are. Now I made a prediction that 0 would not be chosen very often. And did my prediction come true? Do you agree? Nobody picked 0. Nobody picked a 4. But, you know, that worked well. Would you agree I nailed it as far as the 7 went? Right? 7's going to be the most common number chosen. And I said more odd than even. So let's see what that is. 1, 2, 3, 4, 5, 6, 7, 17, 21, 22. And that's odd. And 1, 2, 3, 4 is even. Am I good or am I good? I did that before I seen any of your data. How did I know that that was going to happen? Isabel's freaking out right now. She thinks I can read minds. How do I know that? Am I good at guessing? No. Other people have done these experiments and they have found that when you give people a choice between 0 and 9, they tend to pick, at least in the Western cultures, 7, more than any other number. And they don't like 0. And that, less obvious, odd numbers are more popular than even. What that tells us is that human beings are not very good at being random. See, if I said to Brianna, write down 12 numbers, right? From 1 to 100, 12 numbers at random. Don't do it. But if I asked you to do that, you wouldn't be random, right? You would end up picking certain numbers more often than others, and you would never pick certain combinations. You'd probably never. For instance, would you have written 0, 0 down? Probably not, right? Human beings are hardwired, and unfortunately, that means that we're also hardwired to be biased. So when you ask people to do something randomly and you think, oh, here's 50 people, randomly pick 5 of them. And you'll say, him, her, him, right? You do something like that. And you think, that was totally random. Do you know it's not? You don't know why you're picking those people, but there's all sorts of reasons. Maybe you pick people with brown eyes. Maybe you pick tall people around short people. Maybe you always pick people in the middle. But you see, you make up rules that you don't even know you're making up, which is why people are really bad at being asked to be random. Isabel.
Do like a statistic of like lining up things that are the same, like covering everything except their shoes and then having them all wear the same shoes or something. Like to
You mean you're trying to be random?
Yeah, to prevent this from happening, to do true randomness, could you do that same experiment but just cover everything except their feet?
No, because they would pick people in the middle more than the outsides.
Okay, with like a preference to the left, preference to the right. Okay, so
yeah, all sorts of weird preferences, and it's not always the same preference.
I guess
some people pick the outsides more than the insides, right? But whatever they do, they don't pick it randomly. Except perhaps their partners. They're probably pretty random. It's a miracle to me my wife actually picked me. God, I must be a murderous person to live with. Can you imagine living with somebody who's so scatterbrained as I am? Must be frustrating for the poor women. Right, anyway, where was I? See, perfect example, scatterbrained. Isabel, is that a leftover or you got another question?
That was it.
Are we good?
Yep.
Okay, now I'm going to return now back to the homework for a few moments and let's look at some more of those. And after that, we'll be able to move on to step 2, hopefully, provided that we don't lose power. You can help me any minute. So suppose a statistics teacher, me, asked his students to pick random numbers, and only this time 0, 2, 4, 6, and 8. His general theory is that the proportion who pick the number 0 will be less than expected by randomness, okay? If you just randomly picked a digit from that lot of 5, wouldn't the probability that you pick a random digit be 1 out of 5, which is a decimal, because we prefer decimals, is 0.2. Would that seem reasonable? Right. Now, the null hypothesis would be picking a 0 is going to happen 0.2 of the time. Won't the alternate be that you'll probably pick a 0 less than that? And then you'd go and, you know, you'd do an experiment. You got 500 people and said, pick a number from this list. And you find out the percentage you said 0 was only 0.03. You see that there would be good evidence there to prove what we think is true. People don't pick zeros very often. Right? This one's a bit esoteric, but we're going for it. Confidence intervals and hypothesis testing are the 2 major categories of statistical inference. On the basis of what you've learned, do you think null and alternate hypothesis are statements about the population? Are they statements about the sample? Or are they statements that are using both? From what we've done, does hypothesis testing look like it's only to do with populations, only to do with the samples that you collect, or is it a combination of both being used?
A combination of both.
Good, that's what is the right one, I believe. Better be. We have to shrink this one out. For each of the following situations, write down the null and alternate hypothesis in words. Oh God, these take forever. I'm going to do this one with words, but really I want to focus on the numbers. And then after that, we'll just focus on the numbers and you can read the words later. The way that my brain works, maybe I like numbers, is I take the written description and I go straight to here. I wouldn't normally kind of think about it in terms of English language and then transfer that to here, but that's the way my brain works. Okay. An anthropologist is trying to determine if the people in a certain region are descendant from the same ancestors as those in another region. So you can imagine you're in Malaysia and you're looking at people who live on one island, tribes people live in one island, and you're looking at tribes people 200 miles away on a different island, right? Oh, in America, tell me if I'm wrong, but I believe this is right. Weren't Polynesians, the people of Polynesia, weren't they the people who kept on moving east and landed on various islands like Hawaii and all the other ones that go east? So that you could trace where Hawaiians came from, the native Hawaiians came from, by looking at the genetics of them, and you'd find out that they're basically related to other people from the West. I believe that, isn't that how the Hawaiian Islands get formed? People just way back in the past, sailing east, found an island, and then, you know, lived and grew, and then some of them left that island and went east and so on. So this is what the story's about. So an anthropologist is trying to determine that these people, and she knows that in the region that she's done, 16% of them have a particular unique genetic trait. It could be green eyes, right? Blonde hair, right? Or whatever, right? There are 16% of them have it. She plans to take a random sample of people from this new region and to test them for that trait. If the percentage of the population with the trait in the new region differs from that number, 16, that would indicate that these two populations were descended from different ancestors, right? So they don't share enough in common to be considered like blood relatives, I guess. Now, if you're doing this in English, the null hypothesis is one of these, and the alternate goes with it. I'm going to go for the alternate And isn't that a not equals to story? So in the new region being studied, less than, not going to use you. In the new region being studied, 16 have it, not going to use you. In the new region, less than, not going to use you. In the new region, more than, not going to use it. That's the only one that, as far as I can tell, uses the word different from 16%. Agreed? Right. Alternate, you're not 16. And in the new region studied, equal to. There we go. So the null hypothesis would be 16%. Excuse me. And the alternate would be it's not 16. There we go, not equal to 16. Paul likes certain candy that comes in a bag with mixed colours. The candy company claims that 35% of them are red. So won't that be P equals 0.35? Now, I don't need this English bit, so you can fill that in yourself. He doubts that their claim is true. He thinks that it's fewer than 35. Haven't I now got my alternative? He thinks it's fewer than 35. And I may have to shrink this up so you can see it. There. Now, you see how much easier it is just to go straight to the null alternate than trying to turn it into one of those English sentences and then change it. That's where
There
I'm
wouldn't be an exclamation point.
no, this is a less than. You do the exclamation point if you want to say not equal to.
Okay.
Right. So in this story, it was to do with the tribesmen, and they said, if it's different, different means not equal to. So if it's different, not equal to 0.16. Here he thinks they're giving them fewer than 35%. This is the same story, so I'm not doing that. And now we are moving on to the next guy. Step 2, find the test statistic and all the good stuff that goes with that. Okay, here we are. So we're going to find p hat and test if it's valid to do a hypothesis test. Well, let's assume that we had our data, which we did. Where did I write the numbers? Over here, probably. Okay, I'll do mine. Let's suppose I wanted to do a big version of people don't pick 0 randomly, right? They pick it less than what you would get, right? So we give people, right, 10 digits to pick from, and I get a sample of 200 people. And in that sample, only 13 of them chose 0. You remember p hat, the number who said yes to 200. So that question here is, did they pick 0? And the answer is 13 out of my 200 people did pick 0, which ends up being 0.065. So would you agree getting p hat is pretty much the same p hat as it's always been, right? You get a sample and you ask people, right? So far, so good. Now, the second part is it valid to do that test? There are 3 things that we typically check. We check the size of the sample.
Where did the 13 come from?
I made that number up. So can you imagine I asked 200 students the same thing that we did, and 13 of them picked 0. I know in our case it was 0, so what would that be? 0 to 16. But I want to use this one. So 13 out of 200. So it was made up.
Okay.
Now, size the sample. There's a rule called the 10 rule. Can you remember it? Your sample has to have this property. NP and N1 minus P both have to be greater than or equal to 10. Can you remember that a way back in the day? That's the test. Basically, 10 people have to say yes, at least 10 people have to say yes and no. Now, in my question here, if you did the calculations, can you trust me that NP hat ends up being 13 and the other guy, I'll put it in red. So if you calculated NP hat, so you went 200 times this, you get 13. And if you did this one, you end up with 187. Would you agree that this is okay for sample size, right? It's bigger than 10, we can do it. If we had done a different sample and NP hat was only 2 people, we wouldn't be able to do the hypothesis test. It's far too small, right? And you don't base the sample on N is 10. It's NP hat has to be bigger than 10. So 10 have to say yes. So couldn't you really ask 200 people and still only get 8 of them said 0? And although 200 is a pretty decent size, wouldn't you still fail because that isn't bigger than 10? Does anybody know what the other 2 major things that we typically want to be true when we do a sample? What are the other kinds of things you'd want to be true if you were doing a sample?
Random.
So we would want a simple random sample. And the reason we want that is because don't we want our sample to be a fair representation of the population? Right, so I don't think I could screw up picking the number one, but let's pick a different story. Suppose we were doing the percentage of Republican story. Remember that one where we think it's increased? You wouldn't want to take a random sample if the people you asked were, I don't know, people coming out of a bank. And would you agree they're probably more likely to have more money than not? And so that might influence it. Or don't pick people, I don't know, coming out of an unemployment bureau or something, right? Don't you want your sample to be rich and poor and old and young and fair representation? And simple random sample is typically how we do that. And the second one, which I put in the middle, what other things should you be careful of? In some situations, at least. Any thoughts? You're collecting a sample. You want to make sure it's big enough and you want to make sure it's representative. What else do you want to do? Okay, clue. It's to do with how and what you ask.
Unbiased question.
Yes. Would you agree that in some questions, I don't think would be a problem? Would you agree asking somebody to pick a number, it'd be very difficult to make that biased, right? But couldn't you do political questions and social questions? Couldn't you phrase, you know, hanging and capital punishment and who you're going to vote for? Couldn't they easily, if you're not careful, be phrased in a biased way? So be careful. Are we good? Any questions about that before I move on? Does it feel like a little bit like a lawyer came in today? You know, it's structured in a very specific way. Let's go back. Oh, I'm on the notes. I'm on the right one. Okay. So that's what step 2 is basically about. Find p hat and check that you're allowed to use it. Let's do step 3 now. We're going to find a guy called the p-value. Excuse me. The p-value is the probability. This is, you got the sample. Given that H0 is true. So what's the probability that you got the sample that you had and given the H0 is true? And we call this guy the p-value. The good news is that this value is calculated using SOLE typically. And that is good because it tells me it is a pain in the butt to do it by hand. But let me show you one by hand, just so you can say, okay, I've seen it once. So I'm going to invent a little story. Let's suppose we asked 100 people to pick a random number. Guess I should call it a digit. From 0 to 9, just like you did. And our null hypothesis is 0.1. In other words, the probability that you choose a 0 is 1/10, right? And our alternate is, can we prove that it is less than 0.1? Okay, so that's us done step 1. So far, so good. Now, in one of these stories, there is going to be a piece of information that we haven't mentioned yet. It's called the significance level. And it uses a Greek letter alpha. And the significance level is what percentage of the time are you willing to be wrong? You know you're going to be wrong some of the time, but what percentage of the time, we tend to write it as a decimal, are you willing to be wrong? Can you imagine that that number tends to have 3 specific values? And they're very closely related to a guy you know. Can you remember the 90%, the 95, and the 99? Remember those guys, confidence intervals? 90, 95, and 99. If you turn them on their head, is it not 10% chance of being wrong, 5% chance being wrong, and 1% chance being wrong? So alpha tends to follow that same pattern. It's typically 0.1, which is a 10% chance of being wrong. Another very common one is that one, which is a 5% chance of being wrong. And the last one is 0.1, and that's a 1% chance of being wrong. So let's continue with our step 2 now. We find p hat. Okay, so I went out there and I asked 100 people, pick me a number, and I only bothered to count, because that's all I'm interested in right now, are those that picked 0. Would we agree it's probably going to be less than 10 based on what we did in class? Right. Let's suppose that only 5 out of the 100 Well, let's make it 6, just so it's not all 5s all the way. So 0.06. That is my sample statistic. In this case, that's the, I guess, the proportion who said 0. Here's a puzzle. Is that number significantly less than 0.1? It's hard to tell, isn't it? Can you imagine before formal hypothesis tests were created, wouldn't some people be arguing that that was evidence and others would saying, I don't know, that could happen just because it happens, right? Things happen that are weird. That's one of them. So far, so good. Right, so what we're now going to calculate is the standard error of p hat. So there's a lot of overlap here, isn't there? Can anybody remember the formula for the standard error? You used it in calculating confidence intervals, for instance. Anybody want to commit? Standard error?
Isn't
The it would be p hat times 1 minus p hat, all divided by n.
Correct. Right, does that ring a bell now, guys? You remember that full? Right, okay, so let's move to do the calculation then. P hat is 0.06, 0.94 all over 100. 0.96, oops, put it inside the square root. Square root 0.06 times 0.94 divided by 100, and the answer I get is 0.024, and that's the standard error. And I put a little bubble around it so I can remember it. And I put a little bubble around the p hat. So far, so good. What you do next is you get a guy called the z-score. And there's lots of versions of the z-score going out. They all have the same basic structure, but in this case, it's going to be p hat, take away this fella. Now, do you see that 0.1 there? So it's going to be p hat, take away whatever this number here is. This number here is called P naught. So when you see P naught being used in the formula, it's essentially that number there. So I have 0.06, take away 0.01, all over 0.024. Can you think of that as data takeaway mean over standard deviation? Because it is, right? So in this case,
Isn't P null 0.1 and not 0.01?
it is, thank you. And put a bracket around it. And so it's 0.06, take away 0.1, and divide the whole thing by 0.024. And the answer I get here is negative 1.67. Now, in case you're forgetting what we're trying to do here, we're trying to get a guy called the p-value. And right now, slowly but surely, we are heading towards that destination. So what is the p-value then? The p-value is the probability that you get a z-score less than that number. And you might say, why less than that number? Less than that number. Greater than that number, right? Now this guy, you would get, well, you could do it in your calculator actually, if you've ever looked into your calculator, but there comes a point in time where you have to do it by tables or by salt. And so this guy here, I will get him using salt, so I'm going to try. And see if we can find him. Try to find a salt bun. You never find one when you want one. Okay, where is the salt bun? Okay, I'm going to have to get out of this one and into the next one and find a salt. There we go. So we're trying to find the probability that Z is less than a particular number. Are you looking at chapter 2 here? Right. Let me click on this, Philip. Let's bring them over here. Right. Normal distribution, that's good. Less than, yep, good. The mean and 1 are 0 and 1, that's perfect. All I need to do here is, oh, come on, that is just sheer luck. It's almost the number I want. I want to do negative 0.167. And if you look at the bottom here, that's the p-value. Can you see how much work you need to put into getting one p-value? And the p-value that we got then, write it down, is 0.047. That'll do. 4748. 4747. Got it. And that's how you would do it by hand. We'll show you tomorrow how to do it. Well, in your case, Wednesday, how you can do it using nothing but salt, which is going to be a lot quicker. So step 3 is find the p-value, which is what we've just done here. And we're almost finished this process, thank goodness. Make a conclusion by comparing the value of the p-value with the significance level alpha. So the p-value is like the probability that you get your conclusion wrong. It's one of the ways to look at it. Now, the test that we're talking about here, this conclusion, is basically this. If the p-value is less than the significance level, then there is enough evidence to prove that the alternate is true. So if my p-value is less than the significance level, then I have proved that people choose 0 less than they typically would. Well, my p-value that I just got was 0.047. That's my p-value. Which of these significance levels should I be picking? %, 5%, or 1%? What do you think I should be choosing?
5%.
Right. Well, the answer actually is a bit of a trick question. You shouldn't be picking any of them yet. Because see that alpha? That should have been decided before we've done any of this. Because if you do it the other way, don't you look at the answer and then decide which one you want to pick so you can get evidence, right? That's frowned upon in the statistics world. So actually, right up here, somebody should have said that alpha was, say, let's say they said it was 0.1. Then if that's the case, you are going to check, is this less than 0.1. So are you underneath your tolerance? Yeah, I want to be 10% or less. Yeah. And if you say yes, then your answer will be there is enough evidence to show that HA is true. Suppose that the p-value was going to be compared to 0.01. Would you agree in this second situation, although it's the same storyline, would you agree that that is not true? So if your p-value is less than your tolerance, how much you're willing to be wrong, if the p-value is less than alpha, you will get a yes. And a yes means you have found evidence to prove that people pick zeros less than anything else. On the other hand, what do you think the statement would be if this ends up happening? Can we still say this? No. This is not less than that. And when it's no, you phrase this sentence. There is not enough evidence, and it's phrased slightly differently, to reject H null. So when you do from start to finish one of these stories, your goal is to find the p-value, because once you found it, it tells you if you have enough evidence. And p-values that are tiny is the evidence you're looking for, right? Really, really small p-values. So if you ever look at, if you're in the medicine field or medical field, and you look at surveys and you look at experiments, and they do it this hypothesis test way, which is very common, all you really need to do is look at the bottom, and they will say something like, the p-value in this experiment was 0.006. And you're going to say, yep, you've proved that one. If it's 0.02, well, doesn't it depend on the significance level, whether that's evidence or not? Because if the p-value is 0.02, doesn't that mean that that data could give you a false conclusion 2% of the time, right? You come up with the wrong answer. I think we might have time, even if it doesn't make too much sense. Let's have a shot at doing SALT start to finish. So I'm going to make up a story, and we are going to do a SALT question. Once I get the right button pressed, from start to finish. Okay. So, inferential statistics. One sample proportion, right? Okay, I need a story here, I need something to prove. I think, don't know what I think. I believe that people are going to vote differently in the next election than they did in the previous one. And in my story here, right, here we go. I went out there and I found 55 people out of 100 are going to vote for the Royalist Party. Didn't know there was a Royalist Party, did you? Right? Yeah. When the Royalist Party take over, the Queen's coming back and we're getting rid of all the presidents and that, and she's going to take over, right? And we're going to get back all those states that you stole in the first time round. How many was it, 13 or 11? Come on, you know your own history. How many? 14? Oh, 13. So we're going to get those 13 back. They're just going to go back to Britain, except New York. I don't think I want New York. Right? So we'll take 12 of them back. And we are going to put in here that we think that it is now changed. It's now more than half population. And I think it's a greater than. So that's basically how you type in the alternate hypothesis, that more than half of the people are now going to vote Royalist. And in my sample, would you agree that that looks like evidence that that might be true? Now, when you hit generate results, can you see the P is 0.5? And okay, think of that as the alternate. The alternate is greater. Oh, there's the Z guy. Oh, dear me, do you see my p-value? 0.15. Do you think that's going to be less than 10%, which is the alpha that I'm choosing? Not enough evidence. Suppose I did it again, but it was 1,000 people and 550 of them are going to vote Royalist. Would that change? Would that be able to prove that we're going to win the next election? Oh. How about a Z statistic of 3 and a bit? But look at how tiny my p-value is. Would you agree that's less than 10%? So if I had done that experiment, I would be able to publish something. The Royalist Party is going to win the next election. And people will say, well, how do you know that? Well, wouldn't P be bigger than 0.5 be my evidence? That's all you need to win, right? Be more than half the vote. And my p-value is tiny. And we are done. Say your last name if you haven't already done so.